Boron is often happy with only 6 electrons. What does that mean? When you go to draw BF3, boron's got 3 valence electrons. Each fluorine has got 7, so that's 21. That's 24 total electrons. Boron goes in the middle. You got 3 fluorines coming off of it. Uses up 6. You got 18 left. 2, 4, 6, 8, 10, 12, 14, 16, 18. If it was any element in the middle other than boron, you would have an uh-oh, and you would be short 2 electrons. But since this boron is good, boron is happy with 6. Why is boron happy with 6? Boron is like halfway between helium and neon, right? If you look at the periodic table, boron halfway between helium and neon. What does that mean? The noble gas that comes before it is happy with 2 electrons. The noble gas comes after it, happy with 8. What does boron do? It says, I'll take 6. So that's why boron is an exception for less than 8. Yeah. So don't make a double bond. You know, if you forget it's boron, you say, oh, it's short 2, and you might even do resonance with this. But boron is happy with 6. Let it go like that. So there's boron. I'll give you another boron. Here you have no choice. So another stable boron molecule will be boron trihydride. Why don't you give that one a shot? That's an easy one, BH3. So that's 3 plus 3 equals 6. Boron in the middle, hydrogen, 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 and you're done. You used up all 6 electrons. Boron's happy with 6. It's actually a happy little molecule right there. So boron, only element other than hydrogen and helium who's happy with less than 8 valence electrons around it. But boy, are there a lot that are happy with more than 8. Oh, boy. Any element in period 3 or below can exceed the octet rule by putting extra electrons in empty d orbitals. Copy that down. We'll talk. Here we go. Phosphorus pentafluoride. First thing, it's add up our electrons. Phosphorus 5, each fluorine 7. 7 times 5 is 35. We got 40 electrons to work with. Phosphorus in the middle, and then here's where things get crazy. We got 5 fluorines coming off of it. 1, 2, 3, 4, 5. What? That phosphorus has got 2, 4, 6, 8, 10 electrons around it. How can it be? Take a look at the periodic table, folks. If we look at the periodic table, we look at the periodic table, row 1, row 2, period 3, phosphorus is in period 3. Any element in period 3 or below. So I'm talking silicon, and so we're also only talking non-metals. So look at that staircase there, right? So I'm talking silicon, phosphorus, sulfur, chlorine, arsenic, selenium, bromine, argon, krypton, tellurium, iodine, xenon, astatine, radon. All these cats and kittens, all these guys, period 3 or below, they can exceed the octet rule. They can have more than 8 electrons around them. Where do they put those electrons? They put them in the empty Ds. Here's what I'm talking about. Remember, the Ds have a principal quantum level or energy level, one less than the row they're in. So these are the 3 Ds. Because phosphorus is in the third energy level, it has access to the third energy d orbitals. Now, normally they're just empty, right? But phosphorus can put extra electrons into them, okay? And that's exactly what it does. So any element, it could be phosphorus, could be sulfur, could be xenon, they can take those extra electrons and put them in the Ds that are one less below them. So they go, if I was xenon exceeding the octet, I'd be popping them down here into these Ds. So let's finish this structure off now that we know it's okay. So phosphorus can do this. We used up 10 electrons. We got 30 left. Now, two types of people, thinkers and doers. Each fluorine needs 6 more electrons, and you got 5 of them. 6 times 5 is 30. Phosphorus is already exceeding the octet rule. Let's not put any extra electrons on phosphorus. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. There it is, phosphorus pentafluoride. Let's do another one. How about sulfur hexachloride? Wrap that one up. Give it a shot. See if you can't figure it out. All right. SCl6. We got 6 for sulfur. We got 7 from each chlorine. That's 42. You got 48 electrons. You're going to put sulfur in the middle. What is this? 6 chlorines? It's okay. 1, 2. I'm going to do it like this. 2, 3, 4, 5, and 6. That's 12 electrons around that sulfur. Sulfur can pull that off. Now, 12 is about the limit. Okay, nobody's getting more than 12 around them. Okay, so sulfur is in period 3, so it can take on more than 8. 12 is more than 8. It's pretty full right now. It doesn't want any more. Okay, so you got 36 electrons left. Think about it. Each chlorine needs 6 more, and there's 6 of them. That's 36. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. There's sulfur hexachloride. Sulfur hexachloride is singly bound to 6 chlorine atoms. The sulfur is singly bound to 6 chlorine atoms. The sulfur itself has no lone pairs, but each chlorine has 3 lone pairs on it. Cool. All right, let's do one more of these exceptions to the octet rule, and then we'll get into bond polarity, and we'll come back to this talking about molecular geometries. And Vesper theory and whatnot. Oh, these new markers doesn't want to erase. There we go. Good enough, right? This is a very special molecule, xenon hexafluoride. Why is it special? This is the first time they ever got a noble gas to do anything. Think about it. Look at the noble gases. Noble gases have 8 valence electrons. They're happy. They don't want to do anything. Only way you could get a noble gas to form a bond is if it did exceed the octet rule. So this is the first structure was able to do that. Let's go through this bad boy. At least add up the electrons. We got 8 for the xenon. We got 7 for each fluorine. So 7 times 4 is 28, right? And we got 36 electrons. No, 34 electrons to work with, right? No, I did that right. 36 electrons to work with. Okay, 36 electrons to work with. Pop xenon in the middle. Let's pop the 4 fluorines around it. Here we go. So we're going to do a xenon. We're going to put 4 fluorines around it. 1, 2, 3, and 4. Used up 8 electrons. We got 28. And here is the, so I'm going to let you catch up. Catch up there for a second. All right, now here is something we have never seen before. This is a first, okay? We got 28 electrons. Each fluorine needs 6 more. There's 4 fluorines, that's 24, right? I mean, you could count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Leaves you with 4 electrons left. What are you going to do with those 4 electrons? Now, you have never seen this. We had plenty of situations where you did not have enough electrons. When you don't have enough electrons, that's when you add a bond. Here you have too many electrons. What do you do when you have too many electrons? Let me tell you what you don't do. You don't add a bond. Adding a bond is what you do when you don't have enough. You got the opposite problem here, folks. We got too many. So what do we do when we have too many? Well, those extra electrons are going to go on the central atom. If it can exceed the octet rule, we're going to put 2 lone pairs on that central xenon atom. Here's our xenon tetrafluoride. Okay, each fluorine has got 3 lone pairs. The central xenon has got 2 lone pairs. Xenon tetrafluoride, XeF4. We're going to get into the geometry and all that stuff because we're going to have a square planar molecular geometry. That's all coming. But yeah, we could do one more of these weird guys if you'd like. Okay, again, you haven't really seen that where you had too many electrons and now we got to force somebody to exceed. Why don't you try this one? This one's my favorite molecule of all time. Love this guy. We'll talk about why when we get to the shape. Okay, but why don't you try SF4? See if you can do that one. Let's see how this bad boy went. We got 6 for sulfur. We got 28 for the fluorines. That's 34 electrons. Sulfur in the middle, 4 fluorines coming off of it. That uses up 8 electrons, leaves me with 26. We're going to make the fluorines happy because sulfur's got 8 right now. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I still have 2 electrons left. You see how you have too many? When that happens, if your central atom can exceed the octet rule, you pop it on there. That central sulfur atom has an additional lone pair. This is going to have a seesaw or sawhorse molecular geometry, which is pretty crazy and pretty cool. We'll get to that with the Vesper shapes. All right, let's take a little break from Lewis structures. Not a long one. Not a long one. Then let's talk about the polarity of bonds. Yeah, what's up?
How does that differ from the covalent molecular Lewis structures?
Well, this is still a covalent molecular Lewis structure. You know, this is a covalent compound. These are both nonmetals. This is just one where, under the typical Lewis structure, everybody was trying to get to 8, except for hydrogen, who followed the duet rule. But here, everybody has 8 at this point, but I still have 2 left. So now somebody has got to exceed the octet rule. And now that sulfur's got 10, 2, 4, 6, 8, 10 electrons around it. So this is just an exception to the octet rule covalent molecular Lewis structure. Does that make sense?